we can start. Thanks everybody for joining me for this tutorial on operator theory. Admittedly, if you ask two different people to give a tutorial on operator theory, you'll get two disjoint lectures, I feel like. So this is very, very tailored to very specific questions, which I hope some of you either had or think, oh yeah, that's kind of interesting. It's a good question. And to start off, there are basically three main problems or expressions I want to focus on. And ideally, if time permits, I will try to go through all of them and explain what kind of behind that, what's the idea behind them. So there are three things. First of all, just your regular expectation value. Like as soon as our space is infinite dimensional, what are these objects? What is a trace on an infinite dimensional space? This kind of thing. Then second, the expression of normal states, especially from quantum field theory or from normal algebras and so on, which the question will be, like, we know what a state is. For our state is a density operator, right? But when QFT people talk about states or infinite dimensional spaces, there's usually something different, and the question is, what's going on? Like this will be the hook of this point, and then finally, something we all know and love: the resolution of the identity, right? Which, if this sum is infinite, what does this even mean, or does it even hold in the first place? Right. So these will be the big three fields in a way that I want to cover today. First, a question, just so I can kind of gauge the audience. Who knows what the trace class is, or who has heard of the trace class? Okay, who knows what it is? Okay, so this is a good start then, because this, I think we can all agree that this is at the heart of quantum mechanics or quantum information expectation values, right? And if we're in a finite dimensional space, this is very unambiguous. This is just linear algebra, right? But as soon as operators come into play, so let's say we have some operator A, whatever that means, we want to write the trace as the sum of the diagonal entries in some basis. But if the space is infinite, then quite evidently we can run into convergence issues, and like we need some condition on the operator to ensure that this thing converges, and it also converges independently of the basis we chose, right? So if we choose two different bases, this should give this should converge in both, and this should give the same value, right? So these are the first kind of issues you may run into, or the first questions you may have when thinking about a trace in infinite dimensional systems. And there will be three levels to this. The first one will be about boundedness, then compactness, then the trace class. You don't have to know what any of that means. The idea is simply the further down we go on this ladder, the more of a handle we get on these expressions and on the sum in general, right? So we'll go step by step in order to make sense of what this is, the idea of the first third. Okay, so as a first definition, let's look at a linear map between normed vector spaces. So these don't have to be Hilbert spaces, but they have a norm at least. Just so the following makes sense. And then one defines the operator norm as follows. Take the largest ratio of length of the output vector divided by length of the input vector taken over the full space. So you evaluate this on all non-zero vectors, and the largest value you'll get, at least in the supremum, this you call operator norm. And in finite dimensions, this will always be some number. Intuitively, what this does is it takes the unit ball, right? So all vectors of norm 1 in the domain in X, and it looks at how distorted the ball becomes after applying A. And basically, the biggest distortion, biggest displacement from the origin, this will be this norm. And the problem is that in infinite dimensions, there exist linear operators for which this expression is infinite, which is kind of not good, because this is if you want to make sense of this is the worst case. If this is not even bounded, like if this goes to infinity, obviously we have no chance of making this converge. Let's just maybe say, so if this operator is such that this value is finite, then you say A is bounded. Now, at first glance, you may say, well, sure, you can define this, but this seems like somewhat of an artificial concept to think at like how distorted the unit ball is. And that's a fair point. The interesting connection here is that boundedness is equivalent to something we very much care about, namely continuity. Well, in norm spaces anyway. So the idea is that boundedness encodes the following property. If we have some states that, like a convergent sequence of states, then the operator respects this convergence. And this is what continuity is about, right? Formally, what this means, and this is the first motivation as to why boundedness is a reasonable concept to look at, is that linear operator between normed spaces, again, is bounded if and only if A is continuous in this norm sense. This is like the basis of operator theory. This is usually the first thing you learn about when you learn about operators. Okay. Now, if you come from finite dimensions, you may know this value also as the largest singular value of a matrix. And in infinite dimensions, this will still be true for special class of operators, because there's no guarantee that there's something such as a singular value decomposition. Yes. No, this is just any norm. So in practice, like A could be a quantum channel and X could be the trace class with the trace norm. Then this the operator would only. No, that's fair. Yeah. Yeah, for Hilbert spaces, this will be the singular value. In general, this will be something. That's a fair point. Okay. Right, I already said this. For infinite dimensions, this is always bounded. Like in finite dimensions, linear maps are always continuous. So you usually don't make a fuss about this in linear algebra because it's just a given. Okay, but if we now return to the trace, what this guarantees is A is bounded, then at least the terms of this sum do not exceed this finite value. So that's good, necessary for convergence, of course, far from sufficient. That's the first step. So whatever class of operators we're looking for where this makes sense, they have to be within the bounded operators. Sorry? I didn't. That's right. I mean, this whole trace relies on Hilbert space, right? So everything above here was like normed space, and now I connected it to the Hilbert space case where we care about a trace. Okay, so that's good, but we of course need more. What we really need, like a stronger necessary criterion, is that this sequence, that these numbers go to 0, right? It's necessary for the sum to converge. So what we actually need is that this goes to 0 for all of normal bases of whatever Hilbert space this A acts on. Obviously way stronger than boundedness. And it turns out that this condition is equivalent to something called compactness. And the nice thing is that I don't have to explain to you what compactness is, because it has a very nice characterization, which you're all very well familiar with. Just for completeness sake, compactness of an operator means that the unit ball is mapped to something which is relatively compact. I assume most of you will think, well, yeah, whatever that, you just explain compact with compact. And that's why this Frederik characterization is so nice. Of course, you can just skip this step, don't have to care. Of course, if you care, you can still ask about it, but I'll just take the high road here. So again, we have some linear operator between, well, it could be different Hilbert spaces. For simplicity, I'll use the same one, but in principle, it can be different ones. And there's condition of compactness, which first of all is equivalent to this bound, not boundedness, this condition that the diagonal, like in every basis, the diagonal goes to 0. Call the star. This is equivalent. And what's even nicer, that it's equivalent to the following form. Sj goes to 0. And the F and the G are orthonormal systems. So maybe not an orthonormal basis, but still orthonormal. Okay, and some of you may have noticed this already. This is just a singular value decomposition. And these are the singular values. This would be the quote unquote unitary from the left. This is the unitary from the right. Except these are not unitary, these are partial isometries, but we can just ignore that, whatever. So compactness, this condition we care about, is equivalent to a singular value decomposition where the singular values go to 0. Yeah.
So in this sum and also in the orthonormal basis
yeah.
Condition, there's an index n and j.
Yeah.
And this will always be natural numbers because something your Hilbert space is separable. I don't know.
Yes. Only countably many terms could be non-zero anyway, that's right. But the point is that this H doesn't have to be separable. This can be any Hilbert space. But because of compactness, because of this property, this sum will always be countable. Right? So there's an important distinction. This is independent of the structure of your Hilbert space, unless as long as it's a complex Hilbert space. But you always get this countable decomposition. No, you also get it for reals. I just meant in our case. Yeah.
I have also a question.
Yeah.
Is there an example where what you wrote down NaN goes to 0 holds for one orthonormal basis, but not for all orthonormal bases?
Yeah. That can happen. These are very pathological examples of, like, they rely on Zorn's lemma and the axiom of choice and whatever. So it's
Okay.
this can get very ugly. So you really need, that's a good point, you really need that this happens for all orthonormal bases. That's right.
Okay, but you had to really think hard to construct such an example. Okay.
I mean, I guess if you only want an example where this goes to 0 for one basis, but not in another one, this is kind of easy to construct. Because even if, even in finite dimensions, right? The idea is that through unitary transformations, you can transform this to this. So you can make a non-zero diagonal, as you can make a zero diagonal non-zero by means of a unitary. And you can do the same at infinite dimensions.
Mm-hmm.
So what I was referring to, these pathological examples from other contexts, they would also work here, but this is overkill. That's fair. Yeah.
Okay, yes, I think I see what you mean. Mm-hmm. Thanks.
Any more questions? Yeah. It's only necessary. That's right. Yes. Yeah. No. No, that's the point. Compactness forces that you get this countable decomposition regardless of the dimension of the Hilbert space. Like even for non-separable Hilbert spaces, this is all true. Yeah. Right. So as Philippe correctly noticed and pointed out, this condition does not guarantee that the trace converges, but it was an important step because now it allows us to encode properties of this trace in these Sj, in these singular values, because these Sj are unique. Yes. What do you mean, like this one? No, it does if you have to go to generalized sequences like nets, and then you can make sense of this. Like this, you can also make sense of this if n is an uncountable set, so a non-separable space, if this set is directed. So like the real numbers would be a directed set, so you can make this work. But in the end, it's kind of as Leo as Lev pointed out, only countably many elements of this will be non-zero anyway. Yes, and that's a good point. For non-separable spaces, all of this works perfectly. Okay. Now it turns out using this representation here, which is also called Schmidt representation sometimes, is that this trace. So if I look at this trace as a function from some operator space to the complex numbers in the usual way, and I'm interested in, well, what's the largest space we can put here? What's the largest set of operators where this has all the properties we want, right? Like it's linear, it's well-defined, independent of the basis, all of these things. Then it turns out that here we put something which is called the trace class, kind of motivated by the fact that we want to define the trace on it. And the trace class, it turns out, or first we should define it. So this C of H are all compact linear operators. Sorry, now we have Hilbert spaces, of course. All compact linear operators for which the sum of the singular values is finite, so converges. Right, so because it's compact, we have the Schmidt representation, the singular value decomposition, and then we define the trace classes, all operators which additionally have a summable singular values. And then it turns out the space right here is the largest vector space or norm space, not sure. It's the largest space on which the trace is well defined. So this motivates why this space is called that. And to be fair, this is not obvious. You really have to prove this, but it turns out that this is true. Well-defined means that this sum converges and is independent of the basis. Like it could happen that for two different bases you get two different values. For general operators that can happen, but on the trace class it can't. Yeah. Sorry. Yes, it's right. Yeah, it's not a star algebra, but it's an algebra. Yeah. More general, I'll just drop the name. I will not explain what this means, but just so you've heard it. The trace class together with this norm here, the sum of singular values, it's called trace norm. In sense, it's not only a norm space, but it's a complete norm space. So it's even a Banach space. It's left that algebra has many nice properties. What we care about for the moment is just that we want to define the trace. This is what we need. Yeah. No, it is the. No, sorry, I meant C star. So what I meant is that the trace norm does not have this multiplicative property, or does it? No, it doesn't. So, yeah. Yes, that's right. In the operator norm, it's not closed. No. I guess that's not no, that's fair. Yeah. Yeah, that's fair. Right. So the next point, like we now made sense of the trace, that's good. But here we have a product of two operators. And like at this point, it's not clear yet that if one of these is trace class, for example, the state, then this product is trace class. But it turns out that that's true. So for all trace class operators and all bounded operators, the product is again trace class. For the simple reason, some of you may know this from finite dimensions, because the trace norm has this property where you can split off things, right? Where trace norm of the product, you can split off the operator norm of O1 on the left and O2 on the right. So if O1 and O2 are bounded, these are finite numbers, and this is finite because rho is trace class. So this whole thing is finite. Or I should maybe do this. And this property in literature is called two-sided ideal. Of course, you can multiply with bounded operators and you stay in the space from both sides. Okay, and that's good because so if rho is a state and O is an observable, which are usually self-adjoint bounded operators, product is in the trace class, meaning this expression makes sense. And this is what we set out to do in the beginning. Yes. Just check the time because I have no feeling for that. Oh, that's pretty good actually. Yeah, let me check. Right, of course, the trace has some more nice properties. It's cyclic. That's still true in infinite dimensions. The trace is also bounded by the trace norm, also like in finite dimensions. And I should have written this up there, but I'll mention it now. For all compact operators, the largest singular value, so these Sj are usually ordered decreasingly, so S1 is the largest one. The largest singular value is always the operator norm. So this intuition from finite dimensions carries out to infinite dimensions if you assume compactness. And actually, that's a pretty good rule of thumb. Whenever you do something in infinite dimensions and you think, well, I know this finite dimensional thing, does this carry over? The answer is usually, if you work with compact operators, then yes. It still could be true for bounded operators. Spectral theorem is a nice example. But for compact operators, it takes the form that you know from finite dimensions. So really, the generalization of finite dimensions is compact operators, very hand-wavingly speaking. Yes, that's right. For Hilbert spaces, if you take the operators of finite rank and you look at the closure and operator norm, you get the compact operators. Yes. And the same is true for the trace class if you close in the trace norm. So the finite operators, if you take limits in trace norm, you'll get the whole trace class. Yes. Okay, I think that's everything from this first third. So unless somebody disagrees, and if that's the case, please speak up.
Can I ask?
Please.
You gave a really brilliant intuitive intuition about what are the possible states that I can put in such that this computation that is living sense.
Sure.
Now I'm a physicist, so my quantum mechanics 1 teacher tells me to take the excitation value of O, where O is the derivative. So it's unbounded.
Right. Yes.
So if I give some less restrictions to O that it's unbounded, but something, maybe I can restrict my class of rows such that things still make sense.
Yes, that's right. If you're then you land in the class of so-called Schwarz operators. So that's a fair point. And I should have said this in the beginning. I'm only treating this case where O is a bounded observable. In general, or let's say this is an unbounded Hamiltonian, so this would be an energy expectation value. Then in general, this will not make sense because trace class times unbounded could be anything. Depends on how bad your H is, right? And as I said, there are special cases for certain, like for Hamiltonians which are quadratic in position and momentum. You can define this case called Schwarz operators, for which this makes sense again. But in general, for unbounded Hamiltonians, this is like, first of all, domains come into play, whole different issue. I'll not talk about any of that today. And also for unbounded Hamiltonians, this can become arbitrarily large, right? So in practice, you maybe don't want to look at the set of all states, so all positive trace class operators of trace 1. But you maybe want an additional restriction of having bounded energy, for example. And these states also have nicer topological properties, and they also are physically motivated. But for us, when I say state, I mean trace class, positive, trace 1. Yeah. But this is a nice outlook kind of thing. Please.
If I take, for example,
Yeah. Well, that would be your Hilbert space, right?
Yeah. Like,
Right. I mean, yeah, that's fair. I mean, this is actually I should have. I forgot. I should have done one example, the simplest possible one. So we haven't. Sorry, I skipped that, but I'll do it now. So the simplest possible operator, I would argue, is just the identity, simplest possible non-zero operator. So it just maps X to itself. The question, in which of all these operator classes is the identity? Well, first of all, is it bounded? Check the definition. This is just X. X over X is 1, right? So this is finite. So the identity is a bounded linear operator with operator norm 1. This is maybe the least surprising thing. Now, next thing is a trace class. Well, we can just check the trace here is just infinite sum of the number 1 infinite, so cannot be trace class. Not trace class, because trace of identity is infinite in okay, but now you can ask, is it compact? And you could argue that, well, just look at this expression. And I already said that we have our resolution of the identity, right? So if we just set all these Sj to 1 and Fj equals Gj, then we get this form here. So this suggests that, okay, I guess the identity is compact. The problem is this restriction right here. For compactness, it's essential that the singular values go to 0, which for the identity is, of course, not true. They stay 1 forever.
not the other definition.
I mean, depends on what you mean by other definition. Right, yeah, bounded. You could also take this one, right? This diagonal is just 1 all the time. Does not go to 0, cannot be compact.
Maybe I can add one comment. What you mentioned about the unit ball being mapped to something compact in infinite dimensional spaces, the unit ball is not compact. So the identity maps something not compact to non-compact, so it cannot be compact. This is also
Yes, that's right. That would be an argument why the definition, that's true. That would be another way to see that the identity is not compact. I mean, usually this is my intuition. Right. I mean, that's a good point. Bounded and closed is only in finite dimensions equivalent to compact. So compact always implies bounded and closed, but the other way around is only in finite dimensions. Right? Yes. Yeah, exactly. I mean, that's a definition, right? Every sequence has a convergent subsequence. And in a way, you can also take that as a definition. Like if you just go forever in the space, then eventually you will circle in on one point, or well, a part of your path will circle in on one point. Whereas in infinite dimensions, you could think of something basically, yeah. Like you can take this sequence, right? Like just one on the diagonal and the one goes to infinity. And two different operators of this type will have distance 2 from each other. So they'll never get close. This is an infinite dimensional relic, of course. Actually, this brings me already to the next point. Maybe this was a good question. Yeah. Okay. So the motivation for this one was a discussion I had, like I think a year ago with somebody who said, well, I I read this old paper by Pets, like on the Pets recovery map from the 80s, and I had no idea what he was talking about because the paper was in the language of Neumann algebras. But really, if you know what's going on, you can translate that into the finite dimensional picture. But for that, you'll have to know what's going on. Really, that was my motivation to include this chapter. And if you read these old papers like Pets, Krauss, Davies, whatever, they all do stuff on von Neumann algebras or C-star algebras, whatever. And in every single paper, you will encounter this notion of a normal state. And what they mean by this is they start from a von Neumann algebra. Luckily, I don't have to explain what that is, because Lev will do that in the future, hopefully. For us, we can think, like whenever I say von Neumann algebra, you can just think the set of bounded operators. Right, so in these old papers, whenever they talk about states or normal states, what they mean is the following. They mean a function, a linear function, from this von Neumann algebra to complex numbers, which you may say at first glance, especially from a more modern quantum info perspective, like for me, state is a density operator, square matrix, positive, trace one, whatever. What does this have to do with anything? Right. So this second part is precisely about this apparent gap, which is not really a gap. As I said, it's kind of a translation lost to time, if you will. Okay. As I said, for us, this is just E of H. And the first thing I want to introduce real quick is that these objects that take operators and map them to numbers, they have a special name in operator theory, or the collection of them does as well. So given some general normed space again, normed vector space, and a linear map, then this phi will be called linear functional. So linear functional is just any linear map from a normed space to the complex numbers. And then the collection of all of them will be the so-called dual space. And the point is that for the dual space, we need an additional assumption, which was also part of the bottom line of this first part, in that since we're in infinite dimensions, we have to be very explicit about continuity. We just don't get that for free. So it turns out that you could, in theory, you could look at the space of all linear functionals, nothing added. Then you get the algebraic dual. But what we'll need is the topological dual space. And this is the collection of all continuous linear functionals. And by this result up there, this is just B of X, C. So bounded linear functionals from X to C. This is usually denoted as X star, or I'll use X, X prime. Okay, so this is just the formal language with which to talk about these objects here. And this is also where the states will live, but that's not the full story. Otherwise, this chapter would be kind of short and boring. Now, if we think about that for a second, we might say that, well, we already encountered something like that here, right? We have a formalism to take bounded operators and map them to complex numbers, just expectation values. And indeed, if we take some traceless operator, then this induced mapping by the expectation value has all the nice properties. It's linear. It's bounded. I wrote that somewhere. Yeah, here. It's bounded. I should have written the more general form. Right, so it's linear and bounded, so it's in the space. So if I write this as a shorthand for this mapping here, then the collection of all of these will be in the dual space of the bounded operators by the argument I just made and by the definition. Okay, so you may say, well, that thing up there, these spaces, they in a way encode trace class operators and thus states, right? So that's the full story, question mark. And this is the point where the answer is no, because there's a very, well, pathological is subjective, but there's a gap here. Where this space, because of the axiom of choice, is way larger than this space. But everything in here that you cannot write in this form, you also cannot write down. So it's a very weird kind of thing. But okay, to take one step back, let's quickly look at all the dual spaces of the spaces I just wrote down, so you get an idea of how these are connected. So first of all, the dual space of the compact operators. I think I never defined them, but for me, K is compact operators. This dual space this is precisely the trace class operators using the expectation value. And so this thing right here that we actually care about, that's a smaller dual space. This is dual space of the compact operators. And these form a strict, in infinite dimensions, a strict subset of the space where the von Neumann algebra people states live, at first glance anyway. However, and that's the interesting thing, is that the other way around, it works, right? So the dual space of bounded operators is way larger than what we want, but the dual space of the trace class operators is, in fact, the set of all expectation values induced by bounded operators. So there's this weird, in infinite dimensions, I mean, finite dimensions is all collapsed anyway, but there's this weird one-way street where from trace class you can go to bounded, but you can't go the other way around without getting a lot of noise and nonsense. Sorry? Well, that's only in the infinite dimensional case, yeah. For separable, yeah, yes. Yes. Only in finite dimensions you would have equality. Okay, so but still that's not good, because how do we ensure that we pick one of these functionals, which we would understand as a state, and not something from the junk in here? It's very dismissive. I'm sorry for the other functionals in here, but for me these are whatever. Okay. And the idea how to get back this equality in quotation marks is precisely this identity right here. So we'll add an additional assumption on these states, which will be called normality. That will be the point, which allows us to go back from here to here, roughly speaking. Okay, the idea is based on different topologies on this dual space. If you're not as familiar, that's fine. The intuition behind topology really is like a topology tells you what functions are continuous or what sequences converge. That's what topology is about in the end. And of course, on one and the same space, you can have different topologies, different notions of like this thing converges in this topology, but maybe in this one it doesn't. And maybe to be explicit for a second, if we take this resolution of the identity, then we know that's kind of one of the characterizations of an orthonormal basis, that for every state X, this sum converges the state itself, right? Because it kind of reconstructs the state one by one entry. Right? So in this sense, this resolution of the identity is true if you apply it to a vector. But if you only look at this as an operator on the full space, this is suddenly not true anymore. So identity minus, let's say, the first n terms of this, right? Which if we apply a state to it, this will go to 0 by this thing. But if we look at this in operator norm, this is just 1 always. This does not go to 0. So in that sense, the norm topology is too strong to make sense of this. But if we interpret it element-wise, which we'll learn later what kind of topology that is, then this suddenly makes sense. So really just the point, as I said, I want to make was that for certain objects, there are different ways to say, in which sense they converge, depending on the situation. And in our case, the situation is that we need a topology which is tailored precisely such that we can go back here. That's the idea anyway. Okay, so page, so back in the sense that, like, if I take an arbitrary element in this space, then there's no guarantee that it's of the form that we want it to be. But if I have an additional restriction on this element, which we don't know yet how that looks like, but we want an additional restriction on this element such that we can guarantee that it's of this form. Yes, that's right. And to be fair, yeah, this is the price I pay for being very hand-wavy here. So we'll not look at the dual space with respect to a different topology. What we'll do is we'll introduce an additional topology on the space, which allows us to get back. But the space itself is still the same. Okay, maybe you should just write down the definition and maybe become more clear. Okay, so let's go back to our normed space setting. X is a normed space. And then we already have a sense of convergence, right? Convergence in norm is just that the difference goes to 0. Now I can apply the same thing to x prime. X prime is also a normed space, right? Bounded operator, so it has the operator norm, the normed space. So in this normed space, I could say, or like I could take this type of convergence. So I should write phi. We're now in the space of functionals. What I could also do is the same idea as down here. I could apply it to elements. No, sorry, that was one step too quick. Sorry, we're still on X. I was too fast for my own good. Let's try that again. On this space, we want something weakly. Okay, and what we want is that we don't want convergence in norm, but we want convergence when applying functionals. That was the point. So for all elements from the dual space, this converges in the usual sense, because these are just numbers now. That's absolutely correct. Thank you. Okay, so two different notions of convergence. Yes, well, in absolute value, yes. That's right. And now I can go to the dual space, and I get these same notions of convergence. Like I could have weak convergence in terms of the second dual, whatever that is. But now we want to go the other way. And what this means precisely, this is called weak star. If we have element-wise convergence now. Right, so if something is a dual space of something else, so X prime, and we just introduce a type of convergence where we want the thing to converge on each element individually. Just I mean, these actually are just vectors, or what do you mean? These phi's are bounded, yeah. But that's actually a good point, just a sanity check. Like, why is this called weak? Intuitively, it would be because this is weaker than non-convergence, right? And indeed, if you look at this difference here, and we remember phi is linear, and just, collect the arguments. But phi is also bounded, so this, I wrote it down here. This is by definition of the operator norm, upper bounded by this product here. Right? So if something converges in norm, if this goes to 0, then the smaller thing also has to go to 0. So that's why this is really weak convergence, really weaker than the norm. Yeah.
So weak star is really from like taking the dual and has nothing to do with C star.
Yes, exactly. Yes, good point. Okay. So now we have all these different notions of convergence, and now we have to tailor them such that they do what we want them to, very roughly speaking. So we can just apply this weak star idea to the dual space that we already have a handle on, the dual space of the trace class, because these are just bounded operators, right? So we already know the dual space, which is handy in talking about, or like in making this notion of convergence explicit. Okay, and this is called, and this is really the definition of the section. This is normality, but this is also known as ultra-weak convergence. So let's have a sequence of bounded operators. And then we say this convergence is ultra-weak, or this converges ultra-weakly if it converges in this sense, basically in an expectation value sense. If for all trace class operators, and to be clear, this is the same difference as between weak and weak star, because we could have also applied weak convergence here, but the problem is that the elements from dual space don't have to be of this form, right? So we basically say convergence in a weak sense, but we discard all these elements that we don't want. And then we get ultra weak convergence. Yes.
Like we could just immediately say I think this is the same thing now, but why did we do that?
Well, I guess to give some more background on where this, that's fair. I could have just dropped this, but then this whole notion, at least I felt like wouldn't have made as much sense. But that's fair. We could have just
like a sensible way of how you find a rule or something that makes sense mathematically to do it. Like, you could argue we just don't care about the rule or the vector space or the more fundamental mathematics.
no, this. I mean, for our purposes, like because that's what we care about, we could have just written it down this way. But these functionals, which are not ultra weakly continuous, these are called non-normal states. Also, these do, if I remember correctly, these do come up in some QFT books. So there are some contexts where you need these weird elements. But for us, that's where we could have said from the beginning, we only care about these. And to conclude this point, let me write it down explicitly. So these normal states or ultra weakly continuous states. So do I write it? So the normal elements from this dual, so these which are continuous in this ultra weak sense, so expectation values go through. This is equivalent to this phi being an expectation value for some trace class. So we could have just said we only care about these, but the mathematical reason or the translation between these and the full space or the restriction rather, is this ultra weak continuity or normality. Yes, that's right. And every ultra weakly continuous linear functional is induced by a traceless operator. Yes, so that's a one-to-one thing. Yes, that's right. And to get back to this example, and I'll do so in the third section as well. We already observed that this does not converge in norm, right? But this converges ultra weakly. And yeah.
One addition.
Sure.
So this continuous, it means the map, like the linear function of this continuous with rest, like by this definite ultra weak definition.
Yes, exactly. Mm-hmm. Yeah. Right. So this is a function from B of H to the complex numbers, right? And now we equip B of H with this ultra weak topology. What this means is we want the functional to satisfy the following. We want the talk to satisfy the following. It should be readable. Okay. So what you want is for every sequence that converges ultra weakly, sequence of bounded operators, normality means that this converges as well. Right. So it's basically the notion of continuity somewhere else on these blackboards, where this was the norm, right? This was the usual dual space, and you just weaken this to something else, and then we get this. Yeah. They are on bounded subsets, if I recall correctly, but in general not. That's usually the thing with all these like strong operator topology and all of that. These are usually metrizable on bounded sets or like the unit ball or something. If this Hilbert space is separable as well. All other can of worms, but good question. Okay, yeah, so this example, because they're should have done this first, because then this definition would also have been more clear, maybe. So the claim is that this sequence here, so we cut off at the end diagonal element, that this converges to the identity outer weakly. Okay, so what do we have to check? We have to take the expectation value of this thing with respect to some state or some trace class operator, doesn't matter. So we have this thing. Okay, but this we can just shuffle it around. So this is just the sum of the first n diagonal terms. But Rho's trace class are kind of by construction, this converges to the trace. Which is what we have to check. This has to be trace of Rho times the limit operator, which is the identity. And so this resolution of the identity, kind of by construction of the trace class, converges ultimately. But does not converge in norm, as I showed previously. Yeah, it also converges strongly and weakly, as like everything aside from norm it converges. Okay. Then I'll have one more quick point. If you read these old papers which talk about normal states, which as we now learned are just density operators in disguise in this expectation value sense, they also sometimes drop the term faithful. Like they not only care about normal states, but also about faithful normal states. And I quickly want to write down what this means in the density operator picture. So when they write faithful, what they mean is that it does not vanish on positive elements. So if you input a positive observable and you get 0, then the observable had to be 0 from the start. So this is how they define faithful. Okay, but if you now input the expectation value formalism to translate this to density operators, then what you get is that I skipped one step, but that's the idea. That the state does not vanish anywhere. So in other words, yeah. In other words, faithful translates to the state is positive definite, so it has no 0 eigenvalues. In the same version in infinite dimensions. Yeah.
How would you just define positivity?
Right, so you would define. No, you define it like this. So positive elements are always of this form in C-star algebras. So you want that positive elements are mapped to positive numbers, right? So if you were to mix, if you were to pair a positive observable and a state, you would get something positive against the trace would have to be positive.
So you define the positive for the weekly or you can have any operator, not with the positive number.
Sure. Yeah.
And you could still ask it weekly or monthly.
No. So okay. So there are two different notions. You could either ask about positivity of a bounded operator, which are just positive expectation values, right? Which you could generalize to the trace on density operators. But you don't have to. Or if you look at states, then you want that positive elements are mapped to positive numbers. but none of them, because these are, like for us, this is trace of something, but in general, this can be an abstract dual space object. And that way you don't need the trace. But for us, this is of course the trace. Yeah, Jonas?
Based on that, like, in the sense that, I mean, you can always pick up things like an epsilon, something, so you can.
Yeah, you can, yeah. My point was just that, like, whenever these people talk about faithful, what they mean is positive definite state. So there's no loss of information. Yeah. Yes, that's right. So that's maybe a good point. There's no, it's like one of the properties of the maximally mixed state, the definiteness, which translates to infinite dimensions. That's true, yeah. But that's maybe a good point. I didn't mention this in the first part. When we talked about states, the one important state that does not exist anymore is the maximally mixed state, right? Because it's dimension dependent. If it divide by infinity, that's not good. Fair point. Okay. Yes. No, that's a different. That's different property. Okay. That's fair because strictly speaking, I haven't defined states in this picture. So state is not just an element of this dual space. You also want it to be normalized. So you want it to be positive, but you also want it to be normalized. And normalized means that the identity operator is mapped to 1. Right? And translated to density operators, this means that the trace of rho is 1. Yes, that's fair. So normalize phi of 1.
So now you have all your probability if you don't exist instability.
Yes, because on B of H, you have a notion of positive operators, right? Operators which have positive pure state expectation values. Right? So you have positive bounded operators. So you can say if the input is positive, something positive from B of H, I want a positive output. And this doesn't need. Yeah. I mean, I mean, in practice, because as you know, spectral theorem usually goes via like spectral measure and integrals and so on. And like that's usually a proof tool, right? Like whenever you want to compute things, you usually have an explicit countable diagonalization, right? So for example, you have your like harmonic oscillator or whatever up to some scaling. You have your Hamiltonian, which you can diagonalize in a countable manner. You have to be kind of cautious about what this means, but in principle, in this context, it's easy to calculate expectation values. But in this more abstract sense, where you're like, of course, you can write down your observable in this way, but if you don't know what these E lambdas are, then how would you compute things and integrate over it? Like you can do it, but in practice, just if you have something countable with the sum, it's just easier. Sure. Yeah. So on an abstract level, the answer is depends on what you want to do with it. Depending on the problem, yeah, this can be helpful. Sure. Okay.
Given that we see now elements of which are states or whatever operators that we saw are the ones that are unintuitive, like they don't behave like sort of.
Well, the bounded ones in general.
Whatever examples that are they have.
Yeah, I mean it.
I'll give up them.
And also, as I said previously, like usually the way to translate things to infinite dimensions, if you want the exact formulation as in finite dimensions, you take the compact operators. Like for example, self-adjoint bounded operators have a spectral decomposition, right, via integral over spectral measure, whatever. But it's not. It doesn't look like the thing from finite dimensions where you just use a unitary and you get something diagonal, right? That only works for compact operators because of this Schmidt representation. So explicitly if you want an example of that form, self-adjoint bounded operators can be diagonalized, but it doesn't look like in finite dimensions. I mean, it's a fair question. Again, I feel like it's problem dependent, depends on the context you're in. So let me now tackle the third problem. I think I wiped it away. So the third point, and we kind of answered it already. There's a bit more to it, which I want to tell you about, is in what sense you actually understand this. I already explained that, like in the operator norm, this does not converge, but ultra-weakly it does. But the point is that there are other topologies. One problem of the ultra-weak topology, you could argue, is that it relies on the dual space. Like it's not inherent to the space you're looking at, but you need this auxiliary structure to make sense of what this topology does. So the norm for many things is too strong. Ultra weak non-inherent. You can also argue it's maybe a bit complicated, like I needed one whole blackboard in 30 minutes to introduce this thing. And we can do it in a lot easier manner. And this will also lead us to some language relevant to von Neumann algebras. Like this is also relevant to von Neumann algebras depending on the take, like the path you take. But there are two other topologies which are more common and also more natural for these problems. And the first of them are already T's, right? Because it said, if we just apply an element to this, then this makes sense, this converges, right? And this applying an element to this is in and of itself a topology. It's called the strong operator topology. Let's again start with a sequence of bounded operators and a limit. Strong operator topology just means element-wise. So whatever element I pick, kind of the same as with the like weak star, the same idea. This is just on a more general space, but same idea. We just say for every element, it's convergence. But now you may say, well, I can go one step further, right? Like why? Sure. Weekly. Yes. Yes, yeah. Actually, that would be the next point. So quickly write that down. So there's also the weak operator topology. And now this has a connection to the previous thing. Because you could also say, well, oops, topology, spelling is hard. Could also say, well, if I look at these elements, if I could look at like matrix entries. Oops, so I could also want this to converge on each matrix element in a way. And now this, and that's Riemann, I think. This you can, of course, write as a trace, and this is of trace class because it's rank 1. And this also shows that the ultra weak topology is stronger than the weak topology. Because like you could always have, like in general, you have something of this form, but if you pick something of rank 1 specifically, then it, then it reduces to this case here. Maybe I should draw a diagram. Maybe that's easier. So we are on B of H. We have our norm convergence. Norm convergence, I already showed that, implies that it converges in strong operator topology, SOT here, and WOT here. And if it converges strongly, it also converges weakly. But then there's the other path, the previous topology, right? That norm convergence implies ultra weak convergence. And ultra weak convergence, if we pick the state to be rank 1, roughly speaking, then we get the weak convergence back. So this is the hierarchy of these 4 topologies I talked about today. Very subjective question. I'll say it's definitely confusing to have different notions of weakness depending on like how you look at the space. If you look at it as an operator space or as a just general normed space. Yes. Yes. In that sense, it's confusing. That ultra weak, like by the name ultra weak, you would expect down here, but it's actually here. Yeah. Left.
So this weak operator topology is not the weak convergence in the base sense.
Yes, exactly. That would, I will not draw it, but this would sit here, if I recall correctly. It's between norm and SOTs, the weakly in a Banach space sense. Honest? I don't think to the degree that you would expect it to, but I'd have to look it up. But I think the answer is no. Yeah, I mean, you could start with a more general rant on nomenclature here, as in the word normal means 700 different things in mathematics, right? So calling something normal as your definition is kind of Okay, guess you don't care about the others. Yeah. Honest.
Doesn't what inside
Sorry, say again.
uh,
Oh, I don't. No, I don't think so. No. That's right. So I think if the sums were finite, then it would be equivalent. But I think the point that they're infinite gives a distinction there. Yeah, in finite dimensions, this whole talk never happened because it's all the same. In finite dimensions, there's also only one notion of convergence, right? Because they're all, you can pick whatever norm, they're all equivalent. Nobody cares. Okay. So the final thing, or the final point I want to make are some examples for the last 5 minutes to give you a sense of what these, like what's going on. Basically, what are all these? Why do we care? First example, I'll only do orally because I already explained it. Resolution of the identity, that was the whole point, right? Does not converge in norm, but converges strongly, converges ultra weakly, and does it all converges also in the weak operator topology. So in these senses, the resolution of the identity makes sense. That's the whole point that resolves the start of the section, if you will. Now to other examples, that may be interesting, are the following. One is about Gauss operators. You know, after all, I'm the channel guy, so this is to be expected, I think. So given some channel, we have a Gauss form. I'll not talk about all the specifics, but even in infinite dimensions, this is still true, right? And usually for channels, you have this normalization condition that this is the identity, because then phi is trace preserving. But again, you run into a problem here, as in what does this mean? In norm, you can, I mean, this is already an example. In norm, this doesn't make sense. So whenever you talk about Gauss operators, you usually need the strong operator topology, or one of them, doesn't matter. In this case, they're all equivalent because this is a sequence of positive operators, so that they all coincide, if I recall correctly. So this is to be understood in SOT. And then what this implies, and that's the interesting point, is that if this sum converges in SOT, just something, doesn't have to be one even, then this sum here, which we want again to be a state, a trace class operator, right? Then this converges in trace norm. So if on the Gauss level, on the bounded level, you have this strong convergence, then you automatically get the exact convergence you want from your channel, which is trace norm. You could argue again, it's because it's on elements and not in general, like not the abstract sum, but on elements. This is again strongly, but now in this weird superoperator space. But that's the idea anyway. So another reason why this is a good topology to look at is because it gives you the correct notion of convergence for, say, channels. And another thing, that's the final point I want to make at least, is that if you, let's say you have a unitary operator, so bounded operator unitary, and now you want to approximate it. You want to, I don't know, you want to do computations or whatever. So you can think of your unitary as an infinite matrix if you want, over a separable space. But now, because you only can store finitely many numbers, kind of a U problem, but okay, then like you can only store this block. And your question is, in what sense is cutting off the rest bad? Like what do I lose, roughly speaking? And if this were a trace class operator, then kind of by the Schmidt representation, this block, if we call row n here, just n by n block, then this converges to row in trace norm. But if this is now a bounded operator or a unitary one, doesn't matter, same thing, then this is not norm convergent, but it's convergent in the strong operator topology. So these block approximations are also to be understood in SOT always. Well, the trace norm topology, but the usual, like every norm uses a norm topology. The trace norm turns the trace class operators into a Banach space.
Okay.
Yeah. Okay, and again, the reason this is nice is that in the end, because you don't just want to compute the unitary or approximate the unitary, but you want to apply it ideally even to some state, right? So really don't want to approximate this, you want to approximate this here. So what effect does truncating unitary like this have on the rotation on a state? And what it turns out is, because this truncation converges in SOT on the thing itself, and this is also a sense of SOT on a higher level, this then, oops, not infinity, not good, not good. This is converged to 0. So this, for example, interesting in quantum control, where say you don't have access to the full unitary group because it's big, but you have access to some subset which is dense in SOT. So up to SOT limits, you have everything. But this up to SOT limits can mean you lose a lot of stuff. But still, if you have some target unitary, then you can, so let's say use target. Then regardless of the precision, there's some unitary you have access to, which is epsilon close, written down, which is epsilon close to what you want to implement. But this now depends on the state, and there's no way around that in infinite dimensions. Because if this was not dependent on the state, then this would converge in operator norm. Right? So really, in the case of quantum control, you get these state-tailored unitary approximations for whatever you want to implement. Yes, row is an additional input. That's right. Yes.
All of that follows from
essentially, yes. Yes, because the information you lose is in this block, and this says, for row, this says singular values are small, so you just don't care. Yeah. Okay, that's everything I had. Thank you very much. If there are more questions, I'm happy to ask.